Hello and welcome to another one of these videos. This one is for Lab 11 and the goal is to follow up on Lab 10's video where we created symbolic equations and to show a reason for why we would have created them. This case we are going to be looking at symbolic differentiation and integration, which is a great use of these equations. So we have our heading as normal. In this case, we are going to be looking at position and velocity since that is a common use of differentiation and integration. Now, we're going to start with an equation for velocity, and in this case, that equation is with respect to time. So we create our symbolic variable t for time and our equation velocity with respect to t of 4t times sine of 2t plus 5 times cosine 6t. Once we've created that equation, we end up saying, all right, let's display it and let's run that. So here's our equation. It actually swapped them. Now, once we have this equation like we did last week, let's plug in some values. And we're going to create a list of time values from 0 to 1 in increments of 0.01. And we plug them in to our equation and save that as velocity. With this, let's create a plot so that we can look at how this works. So we create a new figure so that it stays right in here. It's a docked figure, and I just called it Lab 11 video. And we have our plot command. If we run this, we get this plot. Great, we have a line on the plot, but since it doesn't have a title or axes labels, it's pretty useless. So let's add some details to this. We're going to do some of our basic details that we've done before, but we're going to add a couple others in. So now we have our plot of time values, our y values, our velocities. We're going to make it red instead of the default blue, and we're going to give it a name. In this case, we call this f of t, velocity in meters per second. We have our regular title and x and y label commands. We create a grid and we put hold on so that we can add stuff to this plot later. Lastly, we actually add a legend to this plot. In this case, we set the location to be the southeast, which is the bottom right corner. If we wanted it to be in the top right, we would write northeast, or top left would be northwest, things like that. So let's run this now. And we again have our plot here. Now it is red. We've got our legend in the corner, and we've got our grid so that we can see where our axes are 0. Great. We have our velocity all set up. And down here at the bottom, it's been outputted. Once we have velocity, we know that the derivative of position is velocity. So in that case, since we have velocity as the start, we can find the integral of velocity to find position. To do this, we use the int function. And so int of our velocity equation with respect to time is position. And we will output this using our display statement so that we can see. So let's run this. So we took our velocity equation and then we integrated it with respect to time because it only has a single variable currently. This will default to that variable. If you had multivariable, or if you really wanted to make sure it was being integrated with respect to time, you can say comma t, and that will integrate it with respect to whatever variable you had here. So we output that down below and we have our equation. Like we did before, input our values. So we have our time values. We're putting that into the equation, saving that as position, and then we plot it, x values as time, and then our position as our y. We're making this one blue, and we're creating a new name for it. This one is f of t, position in meters. And we update our title to be velocity and position. So we run this and we can look at the graph. Now, we have both on here. We have both in the legend because that will automatically update. but we can check to see, does this make sense? And so we know that if we're integrating our red plot here, our velocity, to get our blue, when blue is close to 0, that means that the area under the curve before it is roughly 0. So we can look and say this first half here up to this point, that's all of our positive values. And then from this point to this point is all of our negative values in our red-lined plot for velocity. So by that measure, we need to be able to say that this part 1 has to be equal and opposite to this part 2. So this is going to be positive, this is going to be total area negative. So we can calculate that. And let's do that. To calculate an integral, a definite integral, from a time to a time, in this case, you would use the same function, the int function, your actual function itself, in this case it's going to be velocity, and then we have an a and a b, and that's the start and end of our equation. So going for that, since that 0.28 is our split, we can say, all right, P1 is equal to the integral of velocity from 0 to 0.28. And then we can calculate P2 from 0.28 to 0.69. Now to output these values, we do what like we did last week, and we put some display statements together. So now let's run this all together, and we can see that for part 1, that is that first part, we end up with a value of 0.885, and for part 2, between that part to the end, it's 0.865 but negative. So that means that this added to that ends up being close to 2. In fact, it ends up being 0.02, and if we highlight that point on the map, it's about 0.02. So that means it does make sense, and that's always a nice thing to check. Once we found that these two are pretty close together, we can move on to the second part of the video. In this case, let's find acceleration. Since we have velocity, to find acceleration, you would take the derivative of velocity. So to do that, we want to differentiate velocity of t with respect to t. And again, you could say with respect to t here if you wanted to, but you can also leave it off. And then we display that and we run it. So now we have velocity, position, and our acceleration. We can check on this acceleration as well. Let's say we weren't sure if that was the correct equation. We also know that if the acceleration is the derivative of velocity and velocity is the derivative of position, we could find the acceleration from position by taking the double derivative. So position with respect to t and again with respect to t. So we can run that and actually output that value as well, like this. And so I called it ACC2 in both cases. We run this, and ACC is equal to that, but that second equation is much longer. So we worry, oh no, did we do this wrong? Are these equations not the same? So we can actually go through and check on them. Let's plug in some values in this case. So we say, all right, acceleration at 0.6 seconds and at 0.6 seconds, we can calculate that for both ACC and ACC2. And we run that now, and we have that they are indeed the same. So these two equations that you see down here, even though they look different, they are equivalent. It's just as it was taking the derivative twice, it built up values that it could have simplified. Lastly, we can plot these values again to check and put them all on the same plot. So the first thing we want to do is we want to plug in our time values into that equation, and we'll go with the first one of these two, ACC time values, and then we can do the same thing we did before, where we say plot of those time values, with acceleration being our y value. Display name, this time we call it acceleration. And in order to put a square into our text string, we do caret and then the braces, and we give it update the title so that it's velocity, position, and acceleration. We run this, we get all those outputs again, and now we have all three plots here, and we can see that acceleration is added onto it. Okay, so that's a quick little example of some differentiation and integration in MATLAB. Thanks.